here I want to do the same problem as before, the one that we did last time, but in this case I want to use the divergence theorem. I want to show you that you can also solve this quite fast if you use the divergence theorem. So we have the pyramid, if you recall. So this is a pyramid, and let me sketch it again. Here we have to integrate over the surface of the pyramid, if you recall. But if we use the divergence theorem, we have to calculate the integral over the volume. So this integral here will become integral of the divergence of this vector field here. So the divergence of this vector x, y, z. And then I have to integrate over the volume. This divergence is very easy to calculate. This will just give me 3, because I have to take the derivative of x with respect to x, which is 1, plus the derivative of y with respect to y, which is 1, plus the derivative of z with respect to z, which is 1. So I have 1 plus 1 plus 1, therefore I have 3. So I have 3 times the volume of the pyramid. And this is just a triple integral. It is quite easy to calculate. So I have 3 times the integral. It's a triple integral. For example, first I can integrate over dz. The variable z goes from 0 to the function f of xy, which describes this plane here, characterized by this equation, and the function f of xy is z. So z is equal to a minus x minus y. So I have to integrate from 0 to a minus x minus y. Then if I integrate over y, I have to take a look at this sketch from above. So I have to take a look at the xy plane, because I have already integrated over z. And here I have this function, which is the projection of the plane, this plane here, x plus y plus z equal to a, onto the y-x axis or xy axis. So this will just be equal to x plus y equal to a. I have to set z equal to 0 because I'm on the xy plane. So I have to integrate from 0 to a minus x if I integrate over y, right? And then I have to integrate over x, but this is a simple integral. I have to integrate from 0 to a because the variable x will range from this point to this point here, which is a, right? This is the maximum value that the variable x can take. And now this is a simple integral that I can perform. So I have 3 times integral from 0 to a, integral from 0 to a minus x of a minus x minus y, dy dx. Then I can integrate one more time over dy, so I have integral from 0 to a of, if I integrate this constant, I will get a times y, and then if I evaluate the constant between 0 and a minus x, this will be multiplied by a minus x. Then I have minus x times the same thing, so I can also factor a minus x here, because this is a constant. This will multiply a minus x. So I can rewrite this result like this, a minus x squared. Okay, so let me repeat it one more time. I treat this one as a constant because I have to integrate over y, and then this will multiply this endpoint here, a minus x. So I have a minus x squared. When I integrate minus y, I will get minus y squared over 2, and when I evaluate it at the endpoints, I will get minus a minus x squared over 2, and then I have to integrate this over dx. And this is a simple integral because it's just 3 times integral from 0 to a minus x squared divided by 2 dx, and this will just give me 3 over 2 times a minus x to the third power with a minus sign divided by 3. And I have to evaluate it between 0 and a, but this thing here will just give me a cubed over 3, so I will get a cubed over 2 as a result. And if you recall, this is the result, the same result that we got last time. Okay, so we chose the orientation of a surface. So I didn't touch on that subject too much, but if you take a look here, we got the same sign that we did last time. And this is due to the fact that we used the divergence theorem like this. In the case of a negative orientation, for example, in the divergence theorem, here you would get a minus sign if you choose the normal to the surface pointing inwards. But if you choose the normal pointing outwards, so that's a positive orientation, you will get plus the divergence of the field times the differential of the volume. So this is some kind of technicality. I don't want to get into these details. It's quite important actually. And you can see that we got the same result as last time.